Thank you. Oh. All right, yesterday, that fourth part, I did super long way and wrong. So I apologize. It doesn't happen very often, but still 20 years in, you start doing something and then you're like, oh man, I don't remember this from last year. And I thought I did what I thought I was supposed to do, but I made one assumption that was super wrong. The assumption I made was that we had the whole mass was the mass of the solute. It doesn't matter, but it's way easier if I teach it the right way. Let's just pretend just the fourth part, which we're good. So the goals to fix what we did yesterday, learn and practice Hess's law problems and start heat of formation. We have a test in 2 days. Now that's pushing it, but it's fine. It's your grade, not mine. So I'm not too worried about it. Oh, I haven't checked my teeth. Pepper in my teeth. Okay, the turkey had a lot of pepper. So here we go. All right, I handed you out this piece of paper that has, oh, don't quit on me. Oops, this thing. What buttholes? Okay, here we go. Steps to solving calorimetry problems. On the test, there's a calorimetry problem. On the test, there's a Hess's law problem. These are the free responses. And there's one on heats of formation. They are different. This is what we did yesterday. And we'll go through it. It should go a lot better today because I looked at it. So anyway, it's color coded on mine. I don't know if you can see it's color coded. Oh yeah, you actually see better on yours because this part's like the answer to part A, B, and C, or like 1, 2, 3 of the questions. Is everyone with me where I want you to be? That one. Yep. Okay. So to solve calorimetry problems, we use this to solve for the joules. M is the mass of the entire solution. And then we convert our answers to kilojoules. Technically on part A, you can leave your answers in joules if you want, but you're going to be asked for kilojoules later. You okay with that so far? Okay, let's look at the problem. We did that one yesterday. Let's actually go to where it says 50 grams of KOH. Weird order, but are you there? 50 grams of KOH, thumbs up when you're there. 50 grams of KOH. Someone hand Daniela the paper she needs. Stop, stop, right there, stop. All right. So there's 2. The other one, anyone have one over there? Okay, over there, where are they? Are we out? Okay, sit. We'll figure it out. Okay, so part A, use Q equals S M delta T. You with me? Yes. Okay, solve that problem. That part I think we were okay with. So you have the grams. It's, remember, water's density is 1. How am I out? I am very confused. Maybe I ran out of paper. I did not run out of paper. Okay, sit. So I'm not out, they're just piled on top of each other. Okay, this is what you need. Okay, who's with me? Who's with me? We gotta be focused today. So A, it wants the heat gained, and remember that's Q. S, specific heat. M, the mass of the solution. Delta T, the change in temperature. We ready? So it is 4.184. The mass is 50 grams plus 300 grams because water's density is 1 gram per 1 milliliter, right? So that's 350. And the change in temperature is just 10. And then you multiply that out and get a value. 14,000, 45, 44. All right, and I'm sure there's a decimal. For now, we're just going to go with that. Raise your hands if you could calculate Q from that type of problem. Okay. You will not be given this. That's something you should memorize. You will be given this. Always, unless it's not water, and then the problem would tell you the specific heat. So if it said like ethanol, and you would read it, and at the bottom it would say the specific heat of ethanol is 2.15. Like it would have to be given to you. But 99.99, 4.184.
Can you explain how you add grams of oil?
Yep. So in your beaker, you have 300 milliliters of water. But we need this in grams. Well, the density of water is 1 gram per 1 milliliter.
Oh.
So you take 300 and you multiply it by 1 and divide it by 1. So because I wanted you to remember that milliliters and grams of water are the same value. And on the AP test, they'll do that. They don't, because no one takes a scale and pours water onto it. We put it in a graduated cylinder, but we know the mass because it's a 1-to-1 ratio. You okay with that? Okay, thank you for asking. All right, so that was 14,000, that'd be joules, correct? All right, or 14.644 kilojoules. That's the answer to the first part. It's just calorimetry math. Q equals SM delta T. Okay, B, what is delta H? Oh, the delta thing's a pain, so I never write it or type it. In kilojoules per mole for the dissolution of sulfuric acid. So go back to your instructions for a second. So on B, it says find the moles of B. Sorry, not B. B is just like a, what do they call that in no.
Footnote?
No, footnote. Thank you. It's a footnote. That's a great question that Tom can't answer. So quit asking hard questions. It's just saying the answer to A or B. So here we go. Find the moles of solute given by dividing the grams by the molar mass of the solute. We've converted to moles a ton before. Now watch. Divide the kilojoules from part A. You solve for above by the moles. That second thing we did to convert the kilojoules per mole. Now, in words, that's a little tricky, but when we write it out, it's not that bad. So this is what I would do if I were you. I would take my answer, which is 14.644 kilojoules. Now, I want an answer over here that's kilojoules per 1 mole, right? Or kilojoules per mole. So I'm going to take this and I'm going to divide it by, you okay if I divide like the sideways part? I'm going to divide it by the moles, but I don't have moles. It gave me grams, right? So what I'm going to do is I'm going to take my given grams, which was 50 grams of KOH, and I'm going to divide that by the molar mass of KOH. Is it 57? So 67, what is it? 56, okay, sorry. Okay, what is this piece? Because I guarantee there's people lost right here. What am I doing right here? I'm finding the moles. I didn't have 1 mole of stuff, right? I didn't have 1 mole. I had 56 of a mole. That's hard to say. But that's what I had because I had 50 grams, but one's 56. So to convert this to kilograms per 1 mole, I just divide, or sorry, kilojoules. I divide my kilojoules by my number of moles. Okay, has anyone done that yet? What'd you get? 16.417. Are we okay with that? So look here. This answer is the heat produced from the given. And that was 50 grams. 50 grams makes 14. But if I had a full mole, that's pokey, which is 56, then it would produce that much heat. So one more time in words, take the answer to part A and divide it by the moles you were given. Now you have to calculate those. Hello, what's up, niece? Did you bring me a Pepsi? Oh, what is it? Oh, you had it covered up. I was like, I haven't had Pepsi in years, but I'll do it just because I love you. Thanks, niece. Good to see you. Yeah, absolutely. Okay, raise your hands if you could do part A. Raise your hands if you can do part B. Okay, so one more time. Part A, SM delta T. Part B, if you want to put it this way, is SM delta T divided by moles. Seth.
Another question. So when you're doing the find the moles part, do you pick the given graph that like consists of?
Yep, it's always of the solute, which will be the system. All right, now, this is where it went a little bit weird yesterday because I don't know what I was doing. It's way easier than I did it yesterday. Way easier. All right, so how many grams of KOH would you need to raise the temperature of 1 liter of the solution, 18 Kelvin? All right, so what we're going to do, oh, by the way, does it say it's the same as water? No. So let's, before we go anywhere, we better turn 1 liter into grams, right? Because SM, M needs to be in grams. So we take the 1,000 milliliters and we multiply it by 1.0 grams per 1 milliliter. Notice milliliters cancel out and I'm left with grams. You okay with that? Okay, we'll come back to this problem, but let's go here. All right, so the third part of this puzzle. We use the picket fence that I skipped a line for some reason. Use the given info to solve for the heat needed, which is Q. How do we solve for Q? Tell your partner, not me. SM delta T, right? Yes. I stole them. That's where they went. Where did I put my pile that I stole? That's not it either. Oh boy, I stole them. And then I walked right there by the water bottle. All right. Looks like we are still short one of them. I'll get you the other one. These will go to better use with you. Sorry. Not sorry though. Okay. So let's do this each part. Use the given info to solve for the heat needed. So go back to your problem. We use the given info to solve for the heat needed. So we have in part C again, Q equals SM delta T. With me? Yes. I took the volume of 1 liter. I converted it to milliliters, which is 1,000 milliliters. You with me? And then I multiplied it by the density, which was 1.08. Okay, so I plug this in to find the heat needed. So I have S, Higley, 4.184, right? Good. Next, The mass, we found it to be 1080 grams. And then the change in temperature, it wants 18. Does this look fun, Megan? Much better. Oh, isn't she sweet? Are you coming to the party on Saturday? Oh, my laws. Oh. You'll go to part of it. Okay. All right. What did we end up with here? Okay, hold on. Jackson, what?
81,336.
Then that's joules. You okay with that? Or 81.34 kilojoules. Are you okay if I just do that? Make it less writing for me? Okay. How many are comfortable solving for Q? Raise your hands. Okay, so we have to find the heat needed. So that's the first part of the third part. I know, like, this is awful, but welcome to chemistry. That's why it's so good for you, is because you have to synthesize a ton of different things into one problem. And you don't love it, but you have no idea how good this is for you. It's like a burpee. A burpee sucks in every possible way, but it works out almost every single part of your body. And that's why we hate it. Okay, here we go. Now, we did that part yesterday. I just didn't do this part very well, like at all. I did it way wrong. I'll admit, I don't have too much pride to admit when I'm wrong. Here we go. Now we're going to use a picket fence. We're going to start it with the heat needed. That's what we just solved for. Okay with that? We need that much heat. And we actually know the kilojoules per mole. And if we know moles, we can find grams. Which we did yesterday, just in the wrong way. Okay, so use a picket fence that starts with the heat needed that we just solved for and solves for grams of solute. Use your kilojoules per mole and your molar mass to complete the picket fence. Okay, that's a lot of stuff. Let's just follow it through. Here we go. This is how much heat we need. 80, okay, that's a green blob. 81.34 kilojoules. What do I want to end with? Grams. When in doubt, picket fence it out. We do not want kilojoules in our answer, right? Do I have a relationship with kilojoules in it? Yes, they are for every how many kilojoules? 16.4 what? 17 kilojoules per how many watts up here? 1 mole. Please, if you're willing, good, that's what I wanted. If you're willing, who feels the same? Like, what? Where did that number come from? Raise your hands. Be like, where the freak did that number come from? Okay, that's a third. It came from us. We found it right here. When we find the kilojoules per mole, we can use the kilojoules per mole. But we got to find it first. That's why it was the second part of the problem, not the third. Okay, now that may have helped. Do we want moles in our answer? No, so they must go here, right? For every 1 mole, is there a relationship between a mole and a gram? The molar mass, right? Which we found to be 56 grams. That will eliminate kilojoules. It will eliminate moles, and it will leave you with grams. Now, if you remember how Healy said to do it, he's right, and it's hidden in here. We found the ratio. That's what we did in these steps. And then the mole ratio is right there. All right, probably a big number, and that's okay. What's that? No, I got a lot bigger number than that. This, you have a plus, that's supposed to be a minus. Does that number look like the right answer? Okay. Now, what if you do this math and you get a negative number somehow? Nope. You just make it positive because we'll never have a negative gram. Because really, long time ago, wouldn't these have all been negative, sort of? It was exothermic. So, but we didn't put the negative. We would have said this many joules released. Okay. You can put a negative, but then you got to remember that there's really Q equals negative SM delta T. Okay. Those are tricky problems. So the first part, we find the heat from a given grams. We use that to find the heat released or absorbed per mole. And then we can use that in a picket fence to solve for grams to produce whatever heat we want. All right. More practice is probably necessary, right? Okay. So this one we did yesterday, but had lots of issues with. So just redo this one on your paper without looking at the notes. Like you can look at the notes from today, but don't look at the answers from yesterday, especially for part C, because I did it incorrect by a lot. Okay. Now, when you get stuck, ask for help. Ask that genius next to you, or ask. All right, so here we go. When we set this up, we had Q equals SM delta T. Someone tell me what they got for A over there. Thank you. We got 9.372. 9.372. And she already made that kilojoules. So then we take our 9.372 kilojoules. We divide it by the moles, which was 30 grams over the molar mass of sulfuric acid. And we end up with, thank you, you're the best, 35.564. Now this answer would have been here, would have been released. All right. Well, that's not what you had. Sorry, my bad. That was wrong. 29. Point what? Okay, sorry. This number comes up later, right? I just looked at the wrong spot. Okay, how many grams? So this one's a few parts. We had Q equals SM delta T. We plug in this for the grams. S is 4.184, 20 is this, and that was the 35, right? And this ends up 35.564. That's the heat needed. So then we set up a picket fence. We know we need that much heat, 35.564 kilojoules. We solved 29.9 here per 1 mole. 1 mole, 98 grams. And then we plug that in and we end up with 113.8 kilojoules. Okay, hopefully we're good there. Okay, the class is already working on this one, but go ahead, pause the video and work on this one. Okay, so A is the one everyone's struggling with. When things dissociate, it just means they break apart.
So there's no reaction.
There is sort of a reaction. It's called the dissociation reaction. KNO3, K plus NO3 minus. That's all you have to do. I know that you want to put water in there, but it's not reacting to water, right? So it's okay. I can sprinkle salt in water and stir it up and the salt dissociates, right? Okay, yes.
But you write a KNO3 solid goes to KNO3 aqueous?
Yeah.
So you don't
They wouldn't love it, but you could get away with that. Yep. All right. So sometimes you may see this. Look at the screen for 10 seconds. Sometimes you'll see a problem like this and they'll put H2O on top of the arrow. That means that it helps the reaction to happen, but it's not a reactant. It's just the place that it's doing it. Okay, it facilitates the reaction. Okay, you're probably still working, but I'll just talk about B. B's from chapter 4, right? NO3. Thank you, Timmy. Besides the problem, how do you know potassium nitrate will dissolve? NO3 minus never precipitates. I don't want to write that because I don't really know how to spell it. Or it's always soluble. Perfect answer. Okay. Yes. Divided by KNO3. Yeah. Okay. So it does ask these questions like the previous problems. Do you need to still see the top? You probably do. You know what? I can just do this. Whoops. Can I? Oh, it's on your paper. What am I doing? It's on your paper. Okay, you're all fired. It's on your paper. But, oh my gosh. Sometimes I'm confused. I should do better today though, because I did not drive this morning, which I'm usually a better teacher when I don't drive. All right, here we go. If you need help on this, please come in the morning. Actually, I won't be here. Please come after school or to B time or ask a friend. I'm just going to go over whatever the answers are you tell me. So how many joules of heat were released in this process or absorbed? What? Oh, it does? Okay, so good point. 2,418 joules. Thank you. All right, delta H for this process in kilojoules per mole. And I know you're like, why does he keep switching? It's for your own benefit tomorrow, I promise. It's to warn you that you better read, which I did not. Thank you guys for pointing that out. All right, so now I just take the answer, right, in kilojoules, whoops, whatever, and divide it by 9 point, whatever it was, 58 over, was it 101? And what do you get there? 20 point what?
25.
Okay, then just the answer here, 74. Okay, we all right with that? Yes. What?
We need to know the density.
No. Whoops, I should go here. Yep. I didn't say it, so assume it's 1. Sorry. Good point. Have a seat. And let's do the other paper. Other paper now. The other paper. Don't lose either one of them. Other paper. Hess's law. Hess's law. Please. I'm going to teach it quick. Review it tomorrow. It's very simple as long as it clicks. So here we go. I'm going to go fast. Don't try and write anything. There's some derivation behind Hess's law. Moving on. Since we know delta H for processes, sometimes we don't have to do it in the lab because we can figure out how each part, the energy change there were for each part and sum them up. All right. Hess's law says the following. This energy change in the stairwell is equal to the energy for each one added together. The sum of all parts equals the whole. Kind of. So here we go. So what it's saying is if we don't know the energy from here to here, but we know the energy from here to here and how many steps we can do the math.
Oh, I see.
Now, it's a little more complicated than that because chemistry always is. All right, but here we go. This is on your paper. So, steps to solving Hess's law problems. Arrange the given reactions. This will make sense when we do it. So that the reactants and products are in the given reactions are on the same side as the products and reactants in the wanted reaction. Just stick with me. So if, in order to do this, if you have to reverse a reaction, change the sign of the enthalpy. If you have to manipulate it, like double it, then you double the enthalpy. Okay, now that is the 2-minute version of how to do this. Now watch the example. So here we go. We do not know this reaction's enthalpy. I said that wrong, but whatever. Enthalpy. But we know that these two have these values. Please focus. So I look, this is the reaction I want. These are the two products, or sorry, two reactions they gave me. So I look at my first reactant and it's solid carbon. In the two it gave me is solid carbon on the left. Yes. Does the coefficient match? Yes. Then I do nothing to this enthalpy. It will stay the same value. Next, don't worry about oxygen. It's everywhere usually. So go to the other one. I need CO on the right. But up here, CO is on the left. So this reaction, I need to reverse. That would put carbon monoxide on the right. Correct? And that's what I want. So if I reverse a reaction, what do I do to the sign of the enthalpy? I switch it to the other sign. Then all I have to do is add negative 393.5 plus 283.5 is around 110. Is that right? Or is that 90? Negative 110. So knowing the enthalpy for parts of reactions that can be added up to form this reaction can help me find my enthalpy. Now I'm really good at reading faces. Some of you are confused. Go ahead.
So since you flipped number 2, there isn't a half oxygen on the other side. Would you have to like do something to the top one?
Nope, because I would have a 1/2 over here, right? And I have 1/2 on one side and one whole one on the other, which left me with my half. None, nothing. Yep. Then if I had more time, if it doesn't, you did it wrong. I'll do it tomorrow. I'll write one out and show you how they all cancel out. Okay, here we go. Next, we have graphite going to diamond. We don't know this enthalpy, but we know graphite going to carbon dioxide and diamond going to carbon dioxide are these things. So I look right here. Graphite is on the left. Is graphite on the left up here? Yes. It only has a 1 and a 1, right? So I leave that alone. Look at me for a second, though. If this was a 2, graphite and graphite, you'd have to double that top one. You okay with that? But it's not. So I have graphite on the left, but diamond is on the left, but I want it on the right. So I have to flip this one. And if you think about what Jackson was saying, we'd have O2 on one side and O2 on the other, and they'd cancel out. And that's why they're not present here. CO2 on one side, CO2 on the other, they would cancel out. So now I don't need to double. I take negative 393.5 and I add 395.4. 1.9. You're telling me it only takes 1.9 kilojoules to make graphite into a diamond? Yeah, that's amazing. No, it's true. So why aren't we cranking out diamonds like crazy? Time. The rate is extremely slow. Okay, here we go. It's harder. It looks scarier. But here we go. Solid carbons on the left. Is solid carbon on the left here? Yes, but there's 2 here and only 1 here, right? So I'm going to double this one. Next, I have H2 on the left. Do I have H2 on the left? Yes. Does the coefficient match? Yes. So I leave this one alone. You with me? I come up here, acetylene, C2H2. It's on the right here, but over here it's on the left, correct? So what do I need to do? I just flip it, which means I change that to a plus. And then I find the sum. What? Yeah, I like it too. It's so easy as long as you get it. There's some people like flip. What the? I don't get it. That's okay. But 28 out of 30, you're probably like, this is not bad. We can do this all day if we have to. Hey, what did we end up with? What? 226.8 kilojoules. Who agrees? Okay. 214. I'm not going to worry about it. It's that number-ish. Thumbs up. Okay, we'll do a couple tomorrow. We have one thing left. It's between difficulty of this and what we did at the start.